Yeah, so my name is Amit Golander. This is my 5th year. I don't hold the record for attending from 2012, but I do hold the record, I believe, for most frequent flyer miles collected during these conferences, so over the years. So I'm here to talk about a missing piece in the puzzle, which we call ZUFS, and is being contributed upstream, well, basically being in the process of being contributed these days. I'll try to explain what it is first, and then the exact status of where it is. So over the last years, I've mainly focused about our own product. Just as background, I come from Plexistore. Plexistore was acquired by NetApp this year. And basically, we were building software for persistent memory since 2013. And it kind of is somewhere here in the middle between, it's not the block-based approach, the easy route, as Andy called it. It's not the SPDK or new programming models approach, although we do support that. The first focus was always supporting legacy applications and allowing them to have all the features that they're used to without developing them by themselves. Features like auto-tiering, I mean, not relying on a single tier of storage like persistent memory. Features like mirroring, features like snapshots, DR, backup, et cetera, et cetera, et cetera. So that has been our focus. The file system is M1FS, or Memory 1 file system. And during the years of developing that, basically, we get a lot of knowledge about this world of software for persistent memory, and obviously. And what we're doing now is basically, because we were aware right from the start that there is a missing puzzle. As Plexistore, we're not big enough to push something like this and dedicate resources to something like this. But what we're doing now is basically repackaging some of our IP and knowledge into this open source component to allow basically the ecosystem, which is very important for the adoption of persistent memory, to allow that ecosystem to basically flourish and see innovative ideas and a rapid adoption. Okay, so basically when you go and implement a new, just sorry for a second, when you go and implement something like that, okay, something like M1FS, PM-based file system that supports storage semantics or a file system that supports DAC semantics for the memory semantics. In either case, you basically need to decide upfront if you want to base your implementation on kernel or in Userspace, right? So that's not different than current file systems, I mean block-based file systems. They also face the same challenge. Some file systems like XFS and ext4 are basically block-based. I'm not talking about the DAX extension of those, but they're basically kernel-based file systems. Every change you want to make to them is really painful. It has to go through, well, it's painful to write it, it's painful to get adopted. If you want to change the DAC semantics, for example, for one of them, that can take years. And then the other choice is basically go back to Userspace. So basically go from the application in Userspace through VFS, have some bridge like Fuse that basically takes you back from the kernel that the system call was basically captured in, back to Userspace to something like Ceph or NTFS or something that's, well, in the Linux world, or some other users-based file system. So what are the trade-offs? Okay, so I guess that's not really news for everyone, but kernel is basically the fastest in terms of access time. That would be the fastest implementation. Okay, while Userspace has different advantages. Basically, it's portable, so you can move between OSs and between versions of OSs more easily. It's resilient in terms that if the file system crashes for some reason, it's not kernel panic. Not the entire machine goes down, basically. Just that process. It's obviously simpler to develop your code and to debug that, which is the basis for all this. I mean, basically, try out new things, innovate on that, see if new ideas catch up, etc. In Userspace. And finally, the licensing, there is no licensing limitation in user space, right? I mean, you do whatever you want, which is also a benefit for some users, right? For us, it's mostly the portable stuff, and personally, for the ecosystem, the innovation, the third one, the innovation, seeing what others do with that, and seeing rapid innovation in the persistent memory space. But in any case, you need to choose one or the other. For hard drives, that's not an issue. I mean, they take forever, so whatever delay you incur in software, that's no one cares. For persistent memory, latency is everything. So there's a problem when you get to it. I mean, the fuse layer, basically the existing bridge from kernel to user space, is just too slow. And I'll show you later some examples. And the problem with that is that it wasn't really an option. I mean, without having a proper kernel to user space bridge that's fast enough and was designed for persistent memory, user space development was not an option on the table, and we took the kernel route at the beginning, I mean, in 2013. Okay, so just to put this in perspective, right, you have it's not 100% accurate. I'm sure others here, Tom, will do a better job later on in putting this into accurate order of magnitude scale. But basically, you have a trade-off between the cost and the density and the latency on the other side. That kind of dictates other technologies that you use alongside that. So one example in the networking space would be TCP versus RDMA, as we heard before. Another example would be the kernel to user space bridge for file systems, fuse, the existing fuse that was designed for hard drives and then kind of improved for flash as an afterthought. And for persistent memory, we realized we need something else. So I'm not going to take you through all, the entire set of performance goals and everything, but basically we want something that we realize upfront that the software itself is the bottleneck. The software latency itself is the bottleneck. So latency, we want to focus around latency. We don't want to create additional copies because each copy, besides of consuming resources, actually also delays us. I mean, copying 4 kilobytes, for example, is 0.7 or something like that microsecond. So that takes up latency, valuable latency. We don't want to do that. So we want to bypass the page cache, whether the user chose to or not. I mean, whether this is storage semantics or memory semantics. In either case, we want to bypass the page cache. We don't want to make another copy. We want to support both I/O or storage and memory semantics at the same time. And just in terms of good engineering, we need to avoid redundant copies, as I mentioned, queues, and we want to remain on the same core that the application ran on. Okay? We want to maintain that affinity in the CPU in order to reach basically few microseconds penalty and not hundreds of microseconds penalty. Okay? So that was kind of the thought process behind the ZUFS. And this is basically the design itself for ZUFS. So ZUFS actually has two different components. One is the feeder, ZUF, that's the kernel component. And then ZUFS is basically the service that's running in user space, right? So you can imagine an application calling some system call. Basically, that gets routed through VFS on the same hardware core, right? Gets routed to VFS, then that calls ZUF instead of a kernel-based file system. And then it basically invokes the service and the file system in user space, right? So this entire path has to be really, really fast. In order to do that, we basically took several design choices. And we have several features to allow easier development of that. And the first thing that's kind of, well, I'm not sure if it's obvious to you, but it's obvious to me when I look at this, is the core affinity, right? We want to use the same hardware thread and basically context switch on the same hardware thread between the application, the kernel side, and the user side, and then all the way back. That way, the data is maintained in the L1 cache. so as close as possible to the CPU. And we don't waste a lot of time context switching and waiting for another CPU to be available on the way. The second most profound assumption here is that we want zero data copy, or to be more accurately, zero redundant data copy, right? So basically the kernel doesn't copy any data at all. The data is copied between those two user space processes. And the way we do that is that within ZooF, we manipulate the page table entries. And that allows, if it's memory semantic, for example, if this is a write system call, basically we allow the file system, the user space file system, to go and read directly the data from the user space buffer and copy that to the persistent memory that it owns. And if this is a DAX, DAX semantics, then it's the other way around, right? We allow basically manipulate the page table the other way around so that the user space process has access to the persistent memory. Okay? That way, there are no redundant copies in the kernel, and the kernel is basically just allowing the control plane for this entire thing. Other things that went into ZUFS are basically things that we developed over time. So efficient access to the PMM device or devices, actually multiple PMM device management of multiple PMM devices, NUMA awareness of those PMM devices, and also a data mover that enables basically moving data from persistent memory to other tiers. And those are just the main examples of several management devices that we put in. In terms of page table mapping, I already mentioned that. So we want to support both of them within ZUFS. So that's easy. It doesn't have to be like in existing file system that you choose up front if you're one or the other. I mean, DAX, memory semantics, or storage semantics. You want to support both at the same time for the same data. So ZUFS supports that as well. And there are some miscellaneous things as well, miscellaneous capabilities, like from time to time you do want to have some asynchronous path. I mean, this entire thing is synchronous. We assume that persistent memory is really, really fast, so we assume we want to do the operation and not go through the asynchronous route, because it's just faster to do the job itself than basically postpone that and have another thread do it in the background sometime in the future, et cetera, et cetera. So that releases resources, CPU, main memory, storage, everything releases resources for other things that you want to do. But from time to time, you do need an asynchronous path. So there are hooks inside that basically, for certain things that I don't know, if there's scrubbing or some error scenarios or things like that, you can basically choose that and delay that type of work to an asynchronous path. On top of that, this is defined as a system service. So basically, systemd in Linux, for example, monitors that and sees that the service is up and running, hasn't crashed or anything like that. So basically, there are a few, I would say, improvements that are unrelated to persistent memory that we took from Fuse as concepts and imported them into ZUFS or ZooFS. Okay, so some proof of why was this effort worthwhile. So let's start with Fuse. Okay, so this is an alternative. Okay, just to clarify that, ZooFS is an alternative way, alternative bridge for Fuse, right? To go back from kernel to a user space file system. It's not better in every mean. It's optimized specifically for memory and persistent memory usage. So we kind of assume you want to bypass the page cache, that your storage is really, really fast. And for that, we also measure the performance for these scenarios, right? So we measure it for direct I/O and using memory. And for that type of use case where you optimize for latency, again, not for throughput or not for something else, for those types of use cases, Fuse, I mean, it starts at relatively high latency, again, for this type of media, right? And at some point, as you increase the load of IOPS, it basically saturates, right? I mean, you see that point here. Basically, fused will not bring you to higher high-ups. So you can't really use that as a bridge, regardless of how fast your file system implementation is. Now, ZUFS, on the other hand, as we design it, it scales with the number of cores that you have. And basically, you see that relatively low latency, right? I mean, it will never be the kernel latency. You still have some penalty there. But relative, I mean, you see that it's lower latency to begin with, and then it scales really nicely with the number of cores that you have. Okay, and actually we think we can actually go and improve on top of that, but that requires additional development that we haven't gotten to yet. So in summary, before I take questions, again, we think ZUFS, well, first of all, ZUFS is the kernel-to-user space bridge for persistent memory. That's what we designed it to do. We're basing our software on top of that for portability scenarios and things of that nature. We open source that basically in order to see, I would guess, to accelerate the innovation around persistent memory and the adoption of persistent memory, accelerate that as well, because I think that would be good for all of us. I didn't put the link to GitHub yet because I'm now within a corporate, and everything has to go all through these review boards, and I'm now on this third review process where I discover the next one every only after I'm done with the previous one. So I think this is the last one. And after that, I was hoping it would be available by now, but probably another week or so, or 2 weeks, we'll see how that goes. But it will be available. The intention is basically to put this upstream. The licensing model for that is really relaxed. I mean, we want this to be adopted in multiple OSs. And when it's ready, I invite everyone to basically review the code, use it, play with it, whatever you seem fit. And if you're coming from an OS distribution, I encourage you to actually adopt that and put that in the distro as well when it's reviewed, obviously, right? So with that, are there any questions?
Hi. So if you've switched over to ZUFS and you've got a system with the persistent memory and you get all these benefits, assuming the system also has some standard NAND flash in the system, and you wanted to continue to use the ZUFS for everything, are the hooks all in place so that that can be pretty decent performance without, or do you have to switch to an old file system when you go to the...
No, so our file system, the M1FS file system now has both a kernel version and a Userspace version. The Userspace version does run on top of ZooFS. It does everything. I mean, it has multiple tiers. It has all the features that you can think of, from one of them is the auto tiering. I mean, that's definitely one of them. I mean, we put most of our capacity actually on flash, not on persistent memory. There's always persistent memory in the system, but we put most of the capacity, not most of the I/O, but most of the capacity on flash or lower tiers, actually. Okay. Sorry? And the file system handles that. Yeah. So it's all based on ZooFS. I mean, we don't have any other hooks that we hide or not going to contribute. The idea is basically that this would be adopted by others as well.
Thank you. Just had a question. The whole file server industry and the idea that this is a new file system. I mean, plus we're talking about persistent memory. I can't help but have this conflict in my head. And so what is that doing to the whole industry, and how is that affecting NetApp's perspective and its user base?
So I think, and this is my personal view, right? Shared storage is great for a lot of things. It allows you to benefit from the economics of shared something. It allows you to operate really easily in terms of you don't need to size exactly how much capacity you need per server, et cetera, et cetera. On the other hand, persistent memory is near memory speed or at memory speed, right, depending on which persistent memory. DRAM is traditionally being placed on the server itself, not across the network, even though we see some different trends now for some use cases. And the concept of what M1FS is doing basically is basically to do a hybrid of those two, right? So have most of your I/O being executed or being accessed and served from the server side, so to benefit from the latency. Right? And the other hand, use the traditional approach, shared storage approaches, and integrate to that seamlessly so that most of your capacity actually comes from shared storage and you don't have to worry about those things. And you do benefit, from data reduction techniques and from DR and from all the existing features that are out there. I hope that answers the question. If not, I get the feeling I'm getting kicked out of the stage, so you'll catch me later, okay? But basically, it integrates well into the portfolio. That's the message.
So now we're going to hear from Neal Christiansen, Microsoft.
So now this is that working? Can you hear me? Forward, backward, and then the pointer if you need it. Thank you. Just an overview of some of the topics I'm going to talk about. And, this is basically the same picture that Andy showed, my version of it. I kind of liked his picture a little better. But basically, I won't go into detail, but basically this is, again, I'm talking about persistent memory in the Windows environment, the work that we've done. And we've modified the NTFS file system to be persistent memory aware. And like we've talked about, of course, not every application is going to change in the world. And so we need to maintain our existing, what we call block mode applications, doing centered file system APIs. And then as we get new applications that do memory mapping, are more persistent memory aware, again, they get this direct access. Andy's talked about all of this, so I won't go into it much more because he did a very nice job. Just so you understand, in the Windows environment, we choose whether a volume is in DAX mode, this direct access mode, or in block mode on top of persistent memory at volume format time. And one of the reasons we choose this at volume format time is because there's actually compatibility issues with various components. These are lists of them. And we actually lose some functionality, and I'll talk a little bit about that in a minute. And today, the only file system in the Windows environment that supports persistent memory is NTFS. This is just a high-level thing. I/O on DAX volumes, if it's memory mapped, you're talking directly to the hardware. And then, as has been talked about before, whether it's non-cached or cached I/O, basically our cache manager does the same direct mapping to the hardware. So there's basically for cache and non-cached I/O, what we call it is one copy access. For memory map, we call it zero copy access because the application on memory map has direct access to it. Now, there is impacts to file system functionality when you have DAX. And again, it comes back to the point that Andy pointed out that there's no hooks in the way. There is no system software doing transformations or any of these things. So you lose software support for things like encryption, compression. One of the features in NTFS is we have transactional file system semantics. We don't support that on DAX as well. We have a change journal. We lose some functionality out of the change journal. And then one of the features that we have is we have the concept of resident files. In other words, they don't actually allocate any clusters. The contents of a file is maintained in our MFT record, equivalent to an inode on Linux. And, but you can memory map directly out of that, and that doesn't work in a DAX volume, so we had to lose this feature. Also impacts on file systems is one of the interesting challenges is you really don't know when a file's changed anymore. When someone memory maps it, you actually don't know if they write to it or don't write to it. All you do know is did they create a read-only mapping or a read-write mapping. And so we had to make some adjustments to how things are handled. And so file modification access times, as well as our change journal, as well as what we call directory change notification to detect changes in the file system. We just make the assumption on a DAX volume that if you create a writable mapping, you're doing it because you're going to change something. So we just update those things at that point in time because that's the best option we have. Now, we do have what we call compatibility mode. In other words, you can have block mode volumes that are fully compatible with everything we've had in the past. No one's really talked about it, but there is sector atomicity guarantees that are made in this environment through a thing called the BTT, or the block translation table. What's nice about this block mode thing is you're running on the fastest hardware there is, but all of your existing file systems, all of your existing semantics, they all just work. But there is some additional overhead because we are going down through an IO stack down to this persistent memory driver at the bottom. And so that is our backwards compatibility answer. It makes everything just work. DAX is, hey, we're moving forward. We're providing new and cool functionality that is even faster than what we get with our block mode compatibility. So let's talk about, so DAX support was first released in Server 2016 on the Windows platform, and it's been out there. But what we've been doing is, obviously, we've continued to make improvements and enhancements since we released that in Server 2016. So I'm going to talk a little bit about some of the things that we've done. So first, we've added several new APIs to flush for doing flushes in DAX mode environments. Specifically, even though you have this nice persistent memory and you can directly memory map to it, there are still CPU caches that are going on, and they're going to get into the way of things. So we actually need the ability to do flushes. And so we do have new APIs that, from both user mode and kernel mode. The user mode ones do not do any transitions in kernel mode. They're doing the flushes directly in user mode, again, for performance reasons. And what's nice about these APIs is that they are designed to work based on the architecture of the processor and actually the implementation. As an example, if someone builds a system that has a battery in it, we don't even have to issue flushes anymore because we know the battery can make certain guarantees. And so these APIs are all optimized based on what's available in the system. And there's documentation you can go look at on these. And this is just a list of some of the APIs that have been added around flushing. We do have this concept of getting a non-volatile token that you then use with these other APIs. The reason for this is to allow us to track information about the DAX region that you're trying to do. It made it more efficient. And the user mode version of the token will make a single call to the OS to get the environment information. But it's designed to be called once for an application, so the overhead of it's quite small. We do have things around flushing versus draining. This allows for parallel flushing. I won't go into detail about what all that means but you can flush multiple regions and then actually wait for the CPU to actually occur. Actually commit those changes to the disk, or not to the disk, to the persistent storage. And so we do separate these concepts of flushing versus draining to allow better parallelism in the system. We have added some very specific new DAX operations. Obviously, we care about NUMA support. So in the Windows environment, we only support a persistent memory volume to reside on a single NUMA node. We don't currently support spanning NUMA nodes for a persistent memory volume. And so we've added a way to query what NUMA node it's on so you can optimize your applications to target those processors on that particular NUMA node. We also have improved bad block detection. We actually have the ability to say, hey, I want to know if there's any bad blocks in this file and which offsets and lengths there are. And so we actually added an API to query this so that you can find out exactly if there are bad ranges in a file and what portions of it, and then your application can deal with that. Now, I'm not going to dig into the details of this slide, but one of the things we've added is large and huge page support. You can read through this on your own, or you can come and talk to me later about why that matters. I'll just tell you this. In talking to our SQL guys, they reached out to me and said, hey, we need large page support because we get a 30% performance boost when we use large pages just over 4K pages. And so it is a big deal. Large pages are basically 2 megabyte contiguous regions aligned on offset and length. And huge pages are 1 gigabyte contiguous ranges aligned on offset and length. And the person that owns the memory manager for Windows, his name is Landy. And as we were talking about the implementation details, he says, hey, beware, these ultra huge pages are coming someday in the future, which are 512 gigabyte pages. So I haven't seen any hardware that supports it yet, but we kept that in mind as we were designing this. Basically, we've done 2 ways to support large pages in Windows. We actually enhanced the file system to support 2 megabyte clusters. In Server 2016, it was limited to 64K. Now it can go up to 2 megabytes in powers of 2. And if you format a volume with 2 megabyte clusters, you just get large page support inherently. It just happens automatically. Also, we had to tweak our environment to align the front of our partitions on 2 meg boundaries. It used to be 1 meg, but if you're needing to align to 2 meg, we had to adjust that. In our latest version of this support, we've also made it so you can actually get large page alignment on cluster sizes less than 2 meg. So we do have that enhancement in place. Now, for huge pages, what we decided to do is we actually ask for an application to tell us if you really want huge pages or not, because it's work to get these 1 gigabyte contiguous chunks and manage this in the allocator. And so we have a new API to request it. There's different options for it. We actually have a primary alignment and a fallback alignment, so you can specify one or both and say, hey, huge is okay, or huge is what I want, but if you can only get large, then that's fine. You can specify whether the requirements are mandatory or not. So you can say, hey, if I can't get it, I want you to fail. And then the application has to decide how to deal with that. Also, you can specify an offset to where the alignment requirement begins. A good example of this is with VHDX files for Hyper-V. The header, if you want huge page alignment, the header is like 2 megabytes in size, and so you want to start the 1 gigabyte alignment not at the beginning of the file, but at the 2 meg mark into the file so that it's 1 gig, or has huge pages from that point on. And again, as I said, our latest, we've done a bunch of updates to the NTFS allocator so that it can manage large and huge pages regardless of cluster size. Now, one of the things after we did all this work, a lot of this work was done for Hyper-V because virtualization really cares about this. They came to us and said, gee, how can we see how a given file is alignment? We started thinking about this. So we had this existing file system control to query file region, so we just enhanced it. So you can actually see the alignment of your file, showing it very nicely, and we actually modified one of our utilities to make it very easy to look at. When we initially did our DAX support, all user data was memory mapped and direct, but our metadata, we still went down to our I/O stack just to simplify the initial port. Well, one of the things that we found is that our performance when we're doing write-through operations, and a write-through operation is basically we persistently commit data and metadata to disk before the operation returns, was slow because of because the journal or the log for the NTFS file system was still going down the I/O stack. So we've done the work to make our journal DAX aware. And this significantly boosts the performance of write-through and just significantly boosts the performance of our logging in general. And the nice benefit is our log updates are immediately durable. And so it's a nice improvement that we have. We've also made some significant changes to our driver architecture. What we had in Server 2016 is this model where we had this single persistent memory disk driver, and then we had this memory bus driver, and this SCM disk driver was the one that's talking to the hardware. Well, as we finished that work and got that release, we decided, hey, there's other architectures coming, and so what we've done is we've replaced this with 2 different drivers. There's basically a persistent memory driver now that is generic across different persistent memory devices. And we have this NVDIMM driver today that we're using, but we can have an NVDIMM, this is really an NVDIMM-N. We can have an NVDIMM-P, we can have a 3D crosspoint driver, whatever it is. So we have an improved driver model going forward to minimize the churn in the system. These are some of the benefits of the new architecture. It's a clear, easier to support new types and a clear separation of responsibilities of management versus accessing the hardware. Also, what they've done is they've made some improvements via PowerShell to actually manage persistent memory, which we didn't have before, and these are different PowerShell commandlets for doing that. Note that these names are subject to change. They haven't been finalized yet, but they are all present in the current version and functioning. One of the other areas that we've improved on is our bad block handling. You know, you would think, hey, it's memory, it should just be robust and never fail, but unfortunately the world always gets to us and things fail. So we have improved it. Initially in Server 2016, the only option available was at boot time, you found out what was bad, and there was no support for detecting things going bad on the fly. The hardware has improved, the infrastructure has improved, and so we do have runtime detection for bad blocks. And so it's really straightforward. If you're doing block type I/O, we just fail those I/Os, just like any other bad sector on any hard disk. In memory mapping situations, if it's not mapped yet, we will just fail future mapping requests, so you just can't map that. If it is memory mapped, we do attempt to unmap it. There are scenarios where the memory manager is unable to, so it is a best effort thing. We hope to improve this over time. I love this slide because I forgot to change it from NVML to PMDK, so sorry, Andy. I did get the memo on the name change, but Tom is gonna, we do have Hyper-V support for memory map files. Tom's gonna talk about that later today. And he's also gonna talk about a little bit more on the Windows PMDK support. I'll use the right terminology now. And we do have support on Windows up on GitHub, so it is available today. This is just the releases that have already gone out that support persistent memory. There will be an upcoming server release. I can't say when that's going to be, but there is going to be a new server release that has all this new functionality in it. And I guess I've got like 2 minutes for a question. I see a question. Go ahead. Oh. Or you just holler, I'll repeat.
Okay. Have you considered placing MFT and other metadata pieces on the PM?
So the question was, have we considered placing the MFT and other metadata on the persistent memory? The MFT is on the persistent memory today. That is where it physically resides. But you are correct that we're not doing a direct mapping to it. And the answer is we absolutely have thought about this, and I think that's our next phase. You know, you might have noticed that Windows is in this really short release cycle, about 6-month release cycle. And so we've got the log done, and so we're looking at doing the rest of the additional metadata files, but that'll be in some future version. Thank you. Question over here.
Just quickly, how much of the functionality that you just described is already in the releases that are out versus what's coming in the next one?
Good question. All of the functionality is in this Windows 10 Fall Creators Update, which is a client release, except the logging change. There will be a release, another client release. If you look at the schedule there, you can probably guess when the next one is. Everything I've talked about will be in that one. And then all of it will be in the next server release, which again, I don't get to say exactly when that is because I'm not a marketing guy, and I can't tell you what the name is going to be because I'm not a marketing guy, but there is a server release coming.
So any of that
Is that in the 1709 server release? Any of the PM stuff that you just described in that?
Yes, a lot of that is, and I can break down in detail which is which. If you want to come and talk to me, I can tell you what's in there. You bet. Thank you. I appreciate the opportunity to come and speak today.